The intense effort to observe, to describe, to understand what's going on in the heavens was largely an empirical endeavor. Ancient astronomers looked into the heavens and saw what was there. But these early efforts went beyond a simple description. Indeed, these pioneers astronomers were amongst the very first people to recognize the power of mathematics in describing nature. It's a great principle of science that empirical mathematical laws describe motions in the heavens and on Earth. Science is a collective human endeavor, advanced by thousands of little-known researchers who collect data step by step, who record them, who publish these data. You'll never hear about these forgotten observers. But relatively few individuals make the great intuitive leaps, and those are the individuals who we justly remember. Consequently, the history of science often must focus on the seminal contributions of a few key individuals and ignore the roles of all those other thousands of individuals who collected data. This is a fact of life in the history of science. We don't know the identities of the ancient astronomers who built Stonehenge or other monuments, but Greek and Roman scholars such as Aristotle and Pliny, of Ptolemy, these are people who are celebrated in their own day, and they're remembered today as well. My objective in this lecture is to introduce four key individuals who transformed our understanding of the heavens. These are individuals, figures of the 15th and 16th century Europe. We're going to meet the Polish astronomer Nicholas Copernicus, who presented a sun-centered model of the solar system. We're going to meet the Danish astronomer Tycho Brahe, who dramatically improved observational instruments in astronomy. And then the German mathematician Johannes Kepler, who analyzed the geometrical characteristics of motions of planets in the heavens. And finally, the Italian physicist Galileo Galilei, who was a pioneer in the development of the experimental method in science. These scientists lived at a time when conventional scholarly wisdom valued ancient authority over experiment and observation. In this context, the Earth was seen as a place of decay, of change. It was placed at the fixed center of the universe, where the immutable heavens surrounded it. The heavens were the place of perfection, circular orbits, fixed positions. All the objects in the heavens were assumed to be perfect spheres. As we shall see, it's the work of Copernicus and Tycho, of Kepler and Galileo that changed the human perspective of our place in this universe. Our first character is the Polish astronomer Nicholas Copernicus, who lived from 1473 to 1543. He was trained in theology and spent nearly half a century working for the Catholic Church. Yet, for reasons that remain uncertain, he devoted much of his life to try to construct a mathematical model of the solar system, a model in which the sun, not the Earth, was at the center. This was a rival hypothesis to the prevailing Ptolemaic Earth-centered model. It's hard to understand why Copernicus did this work. Why would someone who devoted his life to the church spend so much time, his spare time, developing a model that was against church doctrine, putting the sun at the center rather than the Earth? Copernicus seems to have been a very modest man. He studied at the University of Krakow in Poland, and he credited the university throughout his writings for all of his intellectual accomplishments. He said, "It wasn't me, it was just what I learned at the university." He went to Italy to obtain training in medicine and in clerical law simply so that he could help out his own clerical order, so he could serve the community better. He built his own astronomical observatory in his spare time. He made his own records of the positions of stars and the moon, although he's not best remembered as an observational astronomer, rather as a theoretician who developed this new model. A preliminary manuscript version of his heliocentric theory, the sun-centered theory, was circulated as early as 1514, and a few copies of that manuscript survive. Copernicus, however, did not sign his name to the theory, to this essay that he distributed to some friends. Indeed, he never sought personal recognition for this theory, and the theory was not published until right around the time of his death in 1543. Now think about it. This is a really strange kind of hobby, this mathematical tinkering with the cosmos, seeing if you could fit the orbits of planets into this alternate view. His great work is called On the Revolutions of the Celestial Spheres. And in it, Copernicus proposed essentially the modern model of the solar system, with the Earth and the other planets all circling the Sun, while the Moon circles around the Earth. This theory, of course, is in sharp contrast to the Ptolemaic view, in which you had the Earth at the center and the planets circling the Earth with their circular orbits, but also the epicycles to explain retrograde motion. Copernicus noted that for the stars to orbit the Earth, they'd have to be traveling at enormous speed. Far simpler, he thought, for the Earth to rotate on its axis once every day, and then each year represents one orbit of the Earth around the Sun. And that's the modern view. The Copernican model explained most of the retrograde motion of planets like Mars and so forth. And he said that was merely a consequence of the fact that the Earth swings in its orbit from side to side around the Sun. And as it swings back and forth, you see Mars against the backdrop of the stars also moving back, and that explains the retrograde motion of Mars. But the model still relied on perfect circular orbits, because Copernicus was clearly in that tradition. And so he still had to use epicycles, although much smaller than the epicycles of Ptolemy. The Copernican model led to a greatly simplified and more accurate prediction of planetary positions, and that led to his acceptance by many scholars. That, after all, is the true measure of a theory, whether it works, whether it leads to useful predictions. That year, 1543, that's a very pivotal year in science. It also saw the publication of a seminal work on human anatomy, that is, on the fabric of the human body, by the great Flemish physician Andreas Vesalius, who lived from 1514 to 1564. That magnificent volume contains illustrations that were crafted in Titian's studio. It's a wonderful work if you've ever had an opportunity to see the illustrations from on the fabric of the human body. 1543, consequently, is often cited as the dawn of the modern age of science. The Copernican model of the solar system had to be tested, and that task fell principally to the Danish astronomer Tycho Brahe, who lived from 1546 to 1601. Tycho, as he is usually called, advanced the field principally by designing and constructing greatly improved astronomical instruments. This tremendously increased the precision and the accuracy of measurements made on objects in the heavens. Let me tell you about Tycho's life, because it was quite remarkable. He was one of 11 children. He was abducted in childhood by his childless uncle, who was a prominent naval officer named Jørgen Brahe. Jørgen Brahe provided the eager young student with the best possible education, and I suppose, given the fact that his parents had 11 children, they probably really didn't notice that he was gone all that much. I can imagine the Brahe household must have been quite a sight. In any case, Tycho rose to great fame at an early age, and he enjoyed the favors of the Danish king, King Frederick II, who lavishly supported his astronomical research. That royal support, however, did not last throughout Tycho's lifetime. Frederick II died in 1588. His successor, King Christian IV, did not support astronomical work, and it's partly because Tycho was not an easy person to get along with. It's said he was haughty and arrogant with members of the royal family who tried to tour his observatory. So Tycho's own arrogance may have contributed to his downfall. Ultimately, he was exiled to Prague, and that's where he died in 1601. Well, the young Tycho first came into prominence in 1572, at the age of 27, when he discovered a new bright star, a supernova, which is an exploding star. He discovered this in the constellation Cassiopeia, and for 18 months, he detailed the gradual dimming of that star. These observations demonstrated the then astonishing idea that Aristotle didn't know everything there was to know about the heavens, and that the heavens themselves are not immutable, that they can change from year to year. And this added new impetus to the idea you really should study the heavens. This should be an ongoing process as opposed to just taking everything that Aristotle had said on faith. So King Frederick II of Denmark and Norway rewarded him by giving him title to an island, the island of Hveen, which is located between Denmark and Sweden. On that island, the king had built a great castle and observatory, as well as workshops for the construction of the new equipment that Tycho designed. He spent more than 20 years on the island constructing these astronomical instruments and making various astronomical observations. Tycho Brahe's principal task was in improving astronomical observations with new instruments, and then using those instruments to test the Ptolemaic and the Copernican system. He designed devices called quadrants and sextants. These are devices that would locate the position of stars and planets in the heavens. And they were quite different from modern telescopes. They didn't employ lenses. They were just basically glorified gun sights, but very beautifully crafted gun sights. So you'd measure an angle around from the horizon and an angle up and sight a particular object at a particular time and place. And this is just like the exercise I described in the last lecture, where you use a compass needle to get a compass bearing along the horizon. So you use your compass to get one angle, and then you use a protractor as a sighting device to get a second angle. What Tycho did was the exact same thing, but with very elaborate equipment, which were adjusted for contraction, thermal contraction of the core, for example. He had very accurate timepieces to make sure he knew exactly when he was making his measurements. This is what he did. He improved the measurements so that before Tycho, you could measure an angle of arc about 10 minutes, which is like having a dime at perhaps 20 feet away from you. And that's the plus or minus. That's the error of measurement. By the time that Tycho Brahe was finished with his new instruments, you could measure the position of a dime at more than 100 yards away. So imagine this dime 100 yards away and still being able to measure its position exactly. That's the kind of increase that Tycho saw. And so what he did is he'd look first at the Copernican predictions and then at the Ptolemaic predictions, for example, for the position of Mars at a specific time on a specific date. You'd find that position, and there's where Copernicus said Mars should be, and Tycho said, no, it should be over here. Tycho looks, and it's neither. The position of Mars is someplace nearby, but not exactly where either of the previous models said it should be. So what does Tycho do? Just what any good astronomer do. He came up with his own model, which is a rather complex combination of Copernican and Ptolemaic ideas. Tycho's story reveals why improved instruments are so important in science. You can come up with a theory, but you have to make predictions, then you have to test those theories. And often it's an improved instrument with greatly reduced errors that provides new insight. And now we come to the third character in our cast. Upon his death in 1601, Tycho Brahe's data fell into the hands of his mathematically gifted assistant, the German mathematician Johannes Kepler, who lived from 1571 to 1630. Kepler cannot have had an easy childhood. His father was described as, quote, criminally inclined, quarrelsome, and liable to a bad end. His mother was called, quote, garrulous and bad-tempered. Nevertheless, he was an excellent student. He excelled in math and in astronomy. Perhaps in the abstractness of these studies, he escaped the turmoil of his family life. Kepler had become Tycho Brahe's assistant in about 1600, and he carried on that work of observation at the observatories. He kept making measurements of Mars and other planets, for example. But he had an advantage. He was a mathematician, and he was able to take those numbers and fit the path of the planets to a mathematical formula, a mathematical equation. And this is what we'll see as Kepler's great advantage. He saw a great harmony, a great order to the natural world. And he derived three great laws of planetary motion. The first of these laws describes the shape of planetary orbits. Kepler says that planetary orbits are elliptical with the sun at one focus. Now, I want to remind you of the shape of an ellipse and how it's drawn with two foci and a curved path. And so I'm going to do a demonstration now to give you an example of how you can draw an ellipse at home and see how it differs from a circle. You can draw an ellipse at home by taking a board, hammering 2 nails through it, and then taking a loop of string. And all you have to do is just keep that loop taut, and as you go around the nails, you form that curving path, sort of like an elongated circle. And that's the ellipse. What Kepler said was that every planetary orbit is an ellipse with the sun at one focus. That's his first law. His second law is that the speed that the planet travels as it's going around the sun isn't constant. When you're close to the sun, you travel very fast. When you're far away, you travel more slowly. So the equal areas are swept out in equal times. And you've probably seen this idea of the slingshot effect. A spaceship is coming closer and closer to the sun. It speeds up, it goes faster and faster, and it whips around and then comes back. That's the slingshot effect. And it has to do with Kepler's second law. The third law is a mathematical relationship of exactly how fast a planet travels depending on its distance. Kepler's third law is as follows. He said the square of a planet's orbital period, that is, the planet's year squared, is proportional to the cube of the average distance it takes from the sun. So you can see how these laws have placed the Copernican model on a firm mathematical footing. Let me give you an example about how you can use this law mathematically. Let's calculate the distance to Jupiter just by knowing its orbital period, which is 12 years. Because you can make the observation that it takes Jupiter 12 years to travel from one part of the zodiac all the way around back to the same part of the zodiac. And here's how the calculation is done. According to Kepler's third law, the period squared, p squared, over the distance, the average distance cubed, or d cubed, for Earth is equal to p squared over d cubed for Jupiter. Now for the Earth it's easy. The period is 1 year, so 1 squared is 1. The distance is 1 astronomical unit, so 1 cubed is also 1. For the Earth the number is just 1. And that equals 12 squared, the orbital period for Jupiter squared, 12 squared, or 144, divided by the distance cubed. And we have to solve for d here. So d cubed is equal to 144. That means the distance to Jupiter is the cube root of 144, or 5.2 astronomical units, 5.2 times the distance from the sun to the Earth. That was a pretty useful thing to know, and it fell right out of Kepler's laws. In introducing these ideas, Kepler expressed his firm belief that the universe held a great deal of order, indeed mathematical harmonies. In the introduction to his 1619 work called Harmony of the World, which introduced the third law, he says, quote, "At last I have found it, and my hopes and expectations are proven to be true, that natural harmonies are present in the heavenly movements, both in their totality and in detail, though not in a manner which I had previously imagined, but in another, more perfect manner." In spite of this mathematical logic and order that Kepler brought to the universe, he still had to contend with a superstitious world. In 1615, his elderly mother was jailed, and even as he was writing Harmony of the World, he had to go to his mother's hometown and testify and defend her at her trial for witchcraft. At that time in Germany, dozens of people had been tortured and executed for the offense of witchcraft. And so for 6 years, Kepler was forced repeatedly to intercede on her behalf, even at great risk to his own well-being. We now come to the fourth of these famous dead white males, Galileo Galilei, who lived from 1564 to 1642. He's one of a handful of people who transformed both the content of science and the methodology of science. He made major contributions to the fields of astronomy and physics. He devised several ingenious practical inventions, and he was a founder of experimental science. He was the son of a Florentine musician. He was born 1564, the same year as Michelangelo's death, and Shakespeare's birth. He began his schooling in medicine, but soon was drawn to the beauty of mathematics and natural philosophy. Natural philosophy was the word for science back in those days. He was a brilliant thinker, but he could be tactless and arrogant. He thus made many enemies, both among Italian academics and also political and religious leaders at the time. Not a good thing to do in Italy at that time. Many people remember Galileo for his pioneering use of the telescope, which he used to reveal unanticipated imperfections, as they were called, in the heavens. He built his first telescope in 1609, first a 9-power instrument, then later a 30-power instrument, after he heard about the invention in Holland. In Holland, it was just used as a curio, but Galileo realized this could be an important scientific instrument. His first observations were published in a book called The Starry Messenger in 1610. Throughout the book, Galileo emphasizes the importance of modern observations over ancient authority. He promises to reveal, quote, great, unusual, and remarkable spectacles, opening these to the consideration of every man, and especially philosophers and astronomers. This rhetorical challenge really looked at the prevailing Aristotle view and said, Aristotle might be wrong. He might not know everything there is to know about the heavens. We have to look for ourselves. Galileo was the first to observe the craters in the mountains of the moon, imperfections. He saw the compound nature of Saturn, what we now realize are rings. He saw the moons of Jupiter. He saw the phases of Venus. He documented thousands of stars that weren't visible to the unaided eye. He saw 80 new stars in Orion's belt alone. And you realize that the Milky Way is a band of countless thousands of stars that you can't see with your unaided eye. Again, these findings undermined the authority of Aristotle because it showed that Aristotle didn't know everything there was to know. You can make all of these observations yourself with a good pair of binoculars, a 10-power pair of binoculars. You can see the moons of Jupiter. You can see the rings of Saturn. It's really worth doing sometime if you've never done that because they're beautiful sights. You can make the same observations that Galileo made. Now, he was not a mere describer of the astronomical features. Historian of science I. Bernard Cohen describes the power of Galileo's work as follows. Not only did Galileo describe the appearance of mountains on the moon, but he also measured them. It is characteristic of Galileo as a scientist of the modern school that as soon as he found any kind of phenomenon, he wanted to measure it. It is all very well to be told that the telescope discloses that there are mountains on the moon, just as there are mountains on Earth. But how much more extraordinary it is, and how much more convincing to be told that there are mountains on the moon and that they are exactly 4 miles high. Galileo's publication of these discoveries and his bold support of the controversial Copernican system in his dialogue concerning two worlds, that was published in 1632, ultimately led to his famous and frequently oversimplified heresy trial, which took place in 1633. Galileo had earlier promised church officials that he would not advocate the Copernican system, at least not in public discourse. But in that 1632 book, which was published in Italian, not in Latin, which is the scholarly language, he supposedly presents an even-handed account of both this Earth and the sun-centered view. But it really wasn't an even-handed account. The book adopts the literary form of a debate, a conversation among observers of Copernican and Ptolemaic leanings, with an educated layperson sort of sitting around asking questions of these people. Galileo remains, at least in a literal sense, uncommitted, but he puts the arguments of the Ptolemaic viewpoint in the mouth of a narrow-minded Aristotelian and someone who bears resemblance both physically and in terms of rhetorical approach to Pope Urban VIII, who was the Pope at the time. So Galileo's readers knew exactly what his point of view was, and the Pope took great offense, as not a big surprise. So Galileo was convicted of heresy. He was forced to recant the Copernican view, and he was placed under house arrest for the rest of his life, the final decade of his life. He remained at home until his death in 1642. By the way, the Catholic Church officially reopened that case in 1992 and exonerated Galileo 350 years after his death. To many scientists, Galileo is honored first and foremost as the founder of experimental science. Along with many of his predecessors and contemporaries, He sought to understand the mathematical forms, the laws that describe falling objects. This was extremely important in an age when cannons had just been developed and gunpowder and explosives, and you needed to be able to fire objects accurately from one place to another. You needed to know what sort of curving paths objects adopted when they were fired in the Earth's gravity. Aristotle had said that heavier objects fall faster than light objects, and this is a claim that Galileo demonstrated that is quite false. The story that Galileo dropped 2 balls from the Leaning Tower of Pisa, by the way, is probably apocryphal. But nevertheless, he did do that kind of experiment where he'd take 2 objects of different masses and different sizes and drop them from a high place and find that they landed at exactly the same time. So through an empirical experimental approach, he showed that the reasoning, the rationale of Aristotle was wrong. Realizing that free-falling objects move too fast to measure with any sort of conventional techniques of the day, there's the watches and clocks that they had available at that point, Galileo devised an ingenious adjustable ramp to dilute the effects of gravity. This is called the rolling ball experiment, and I'd like to share that with you in just a moment. The main problem with the rolling ball experiment is that you need accurate time measurements. And in Galileo's day, there weren't really any accurate timepieces. You didn't have watches, you didn't have stopwatches or clocks of that sort. At first, Galileo used his pulse, but that wasn't very accurate. And then he invented an ingenious way to measure time. He said, quote, "We employed a large vessel of water and placed in an elevated position. To the bottom of this vessel was soldered a pipe of small diameter giving a thin jet of water. And we collected this water in a small glass during the time of each descent. The water thus collected was weighed after each descent on a very accurate balance. The differences and ratios of these weights gave us the differences and ratios of the times." Galileo and his assistants conducted numerous repetitions, another aspect of experimental science. Let me read you another quote. "In such experiments repeated a full 100 times, we always found that the spaces traversed were to each other as the squares of the times, and this was true for all inclinations of the channel along which we rolled the ball." Let me do just a couple of examples of this rolling ball experiment to show you what Galileo did several hundred years ago. Galileo realized that objects fall straight down much too fast to record how they fall. So he invented an experiment, an inclined plane, which diluted the force of gravity. What he'd do is measure a distance along the inclined plane and then time the fall. 0, 1, 2, 3, 4, 5, 6. It takes 6 units of time to go the entire length. And you might guess, well, then it would take only 3 units to go half as far, marked here. Let's try that. 0, 1, 2, 3, 4. But it takes 4 units, not 3. You have to go all the way down here to only a quarter of the original length. And here, 0, 1, 2, 3. 3 units to travel 1/4 of the distance, 6 units to travel the entire distance. So distance is proportional to the square of time. That was Galileo's great discovery with the rolling ball experiment. A fascinating aspect of this experiment is that Galileo did not conduct the rolling ball experiment to discover a mathematical relationship between time and distance. Rather, he used the apparatus to confirm his conviction that velocity and time bear the simplest kind of relationship to each other. That is, the velocity of a falling object is proportional to the time of its fall. He called this steadily increasing velocity uniform acceleration. Galileo also demonstrated mathematically that this result was equivalent to saying that the distance traveled by a falling object is equal to the square of the time of its fall. Galileo devised lots of other experiments in his study of terrestrial mechanics, and you can repeat some of these yourself. One of the most famous is his study of pendulums, and I'm not going to go through all of his apparatus, but you can do this at home. You can take a stopwatch, you can have shorter pendulums, you can have longer ones, you can put different weight masses on them and see what happens. What you'll find is that longer pendulums swing more slowly than short ones, but that the rate of speed is independent of the mass of the pendulum. That's the sort of thing that's fun to do at home, and try various objects with your kids if you can. It's a great thing to do at home. Galileo also discovered a key principle regarding ballistics, that is, the way objects fly through the air. He found that horizontal motion of a falling object is independent, completely independent of the vertical fall. For example, he cited the example of a heavy object dropped from the mast of a moving ship. Aristotelian philosophers held that an object would land some distance behind the mast of the moving ship. If you dropped it high up, the object would sort of fall backwards, if you will, and the ship would move out from under it. But Galileo said, no, the object's moving along with the ship, then it's going to fall right at the base of the mast. He tested these ideas experimentally, for example, by firing cannonballs horizontally off a cliff and observing the curving path of the fall. And what he found is when you do that, you come up with a curved path called a parabola. And that curving path you see over and over again, that's the curve of falling objects. To summarize this lecture, we've met four key scientific figures of the 15th and 16th century. We've seen Polish astronomer Nicholas Copernicus, who developed a model of the solar system in which the Earth orbits the Sun. Danish astronomer Tycho Brahe, who tested the Copernican model with dramatically improved astronomical instruments. The German mathematician Johannes Kepler, who derived new mathematical laws for the movement of planets in their orbits. And finally, the Italian physicist Galileo Galilei, who developed a mathematical description of motions of objects at the Earth's surface. Galileo's empirical laws of terrestrial motions, which describe curved paths of moving objects near the Earth, and the mathematical relationships of distance and velocity and time, are not unlike those of Kepler in his descriptions of the orbits of planets. But it remained for Isaac Newton to merge the empirical laws of Kepler and Galileo into one set of universal laws of motion. And that's the subject of the next lecture.